Hello, physics students. This is Mr. Bornheimer, and today we're going to have an introduction of two-dimensional motion. Um, I wanted to create a video for this because, first and foremost, this is not the easiest of subjects in physics. There's a lot of intricate math involved, and you have to remember a lot of things that we've already talked about, some of those things that were challenging in and of themselves. Another thing that also comes into play here is a much more advanced version of trigonometry. So we're going to be spending a fair bit of time today talking about these things and working on them. If you want to go ahead and grab a blank sheet of paper and you can work through some of these problems with me, that'd be great. All right, go ahead and do that now. All right, here we go. We're going to be looking at, okay. So I'm going to go ahead and draw, a ramp. And there's the ramp. And I'm going to make a line that represents a horizontal, essentially kind of like the ground. I'm going to make it dotted in green, kind of maybe to represent grass or something like that. And I'm going to go ahead and make this 10 degrees. It doesn't really matter what angle you choose for this type of problem. Ultimately, though, this angle is going to play a very large role in how we analyze the problem. So just make sure that you keep that in mind. And we're going to call this angle, I'm just going to call it theta. Now I'm going to go ahead and draw a box. And we'll just go ahead, I'm going to make that box kind of like a green color here. And that box is on the ramp. Okay, there it is. And the box is going to weigh somewhere in the neighborhood of 2 kilograms. Okay, so anytime we introduce a new number, I'm just gonna kind of put it up here in the corner. So it's gonna be 2.0 kilograms. And the angle so far is 10 degrees. First thing we need to do when analyzing a problem like this is we need to go ahead and we need to draw all of the essentially all of the forces acting on this particular box. So first of all, we have gravity, and that's acting downward. We also have a normal force, which is acting upward, and it's perpendicular to the surface. And we also have friction, which is going to provide a little bit of resistance in the direction opposite the direction opposite that in which the box is trying to be pulled. And because gravity is pulling down the box and it's going to be pulling ultimately in a direction kind of in this direction, okay, then we are going to go ahead and trying to undo that. Oh, well, it's not working for me, so we'll go ahead and just erase it. Ultimately, friction, this little force here, is going to act opposite our motion. So we have the normal force here. This is the force normal. We have the force of friction. And we have the force of gravity. So we have these three forces acting on our box. Now, if we think about this box and the way it's situated, we can go ahead and we can almost maybe we want to think about it as being on a flat surface. So I'm going to go ahead and advance to the next slide here just to kind of give you a perspective on what I'm talking about. Let's say that we have, this is really the ramp, but we've rotated it sideways. And here is the box which we were analyzing. Okay. And the force of gravity, or the normal force, was acting upwards. Okay, and friction was acting to the side. But you'll notice from our previous diagram that gravity is a little bit like shifted left at an angle from the normal force. So it would be kind of transposed in this direction. Okay, now you'll notice there's no force that directly opposes the normal force, and there's no force that directly opposes this force right here, which it would be the force of friction. If the object is stationary, we know that the net force acting on the object, okay, for a stationary object, has to be 0. So if the object is stationary, F net has to equal 0. So there has to be some force that is equal and opposite to friction, okay? Maybe in this direction. And there has to be some force, let me do a highlighter here. And we'll go with yellow here. There has to be some force acting in this direction, and there has to be some force acting in this direction to counteract the normal force, and a force acting in this direction to counteract friction. Now, if you recall from when we were talking about vectors, there is something called component vectors. And if you take a close look here, you will probably notice that these vectors, this vector here and this vector here look a lot like components of the force of gravity here. So, with that being said, really we can analyze the force of gravity by breaking it into its component vectors. And we're going to go ahead and do that on the previous slide. I'm going to go ahead and I'm going to select some lines here, but I'm going to go ahead and make them a different color. We're going to go with purple, and we're going to go with the line style to being dotted. Okay, we're going to go with a very fine dot. So what we're going to do is we're going to say that the component here, we're going to move that so it lines up nicely. Right there. And there's also a component in this direction as well. Okay, now, because these components are in essence in line, like this one here is in line with the ramp, and this one here is opposite the normal force, we're going to go ahead and define a coordinate system. And our coordinate system is going to be defined by using kind of these arrows here. I'm going to call this the y, negative y, x, negative x. And so ultimately, this is going in the negative y direction, and this is going in the negative x direction, whereas the normal force would then be positive, and friction would be positive. Okay, now remember, the object is stationary. So all of the forces acting on it have to cancel out. If the object were moving, it would be different. Now, because of some geometry and looking at triangles and whatnot, it can be determined that theta, okay, would be this angle in here. This can be theta. And if that is the case, then we're really working with something very much like, and I'm going to go ahead and select several items here. I'm going to go ahead and I'm going to copy them. I'm going to take them to a new slide. And I'm going to make them bigger. Okay, so we're just going to go ahead and make them bigger so that we can kind of get a better perspective on what is actually going on here. Okay, so we have the force of gravity acting down, and we have theta, which is right in here, and theta is equal to 10 degrees. And the force of gravity is entirely dependent upon how much the block weighs, which in this case is 2 kilograms. So we're going to go ahead and start to analyze this situation. The force of gravity is going to be equal to mass times gravity. And for our purposes, we're going to say that gravity is equal to 10 meters per second squared. And because it's acting downward, it's going to be a negative 10 meters per second squared, because we've defined anything in the downward direction here as being negative. So I'm going to have 2 kilograms times a negative 10 meters per second squared Okay, and that ends up giving me a negative 20 newtons. Okay, so all of that is going to be here. It's going to be a negative 20 newtons. And now that you've seen it, I'm just going to go ahead and erase it to kind of conserve space. Now, this is a trigonometry problem. This is really fg of x because it's in the x direction as defined by our coordinate system, x in this direction, which is here. And this is in the y direction, so it's fg of y. Fg of y is really opposite the normal force, so the negative actually represents opposite the normal force, and Fg of x is really negative, is opposite the force of friction. So really what we're going to do here is we're just going to calculate what the opposite of friction is and what the opposite of the normal force is, and in doing so we essentially will find the normal force and the force of friction. Okay, so the next one I'm going to do is I'm going to go ahead and set up some trigonometric properties here. In order to analyze a right triangle using one angle in the hypotenuse, you need to refer to your SOHCAHTOA. Oops, I gotta go ahead and erase that. Now, because we're working with the adjacent and the opposite, okay, and we're trying to find the adjacent and the opposite, we're probably going to ignore the tangent here. And we're going to focus on these two. The angle doesn't change, so we're going to go sine of 10 degrees. Make sure that if you're working with a calculator that has the option of radians, that you do not choose that option, that you have your calculator in degree mode when doing problems like this. So then you also have the cosine of 10. Sine is equal to opposite over hypotenuse. Well, opposite the angle would be this side right here, which is fg of x, so which is really the opposite of force of friction. So I'm just going to say that it's the opposite of the force of friction over the hypotenuse, which is a negative 20 newtons. Okay, now cosine is the adjacent, which is the opposite, the normal force, over negative 20 newtons. Okay, and we'll do some quick calculations here. Okay, so what we need to do here is you just multiply sine of 10 by negative 20 and cosine of 10 by negative 20, and it'll give you these. If you want to, you could actually even just drop the negative signs, because ultimately what happens here is they become positives, because you have negatives in both the numerator and the denominator. So if you have, I'm just going to go ahead and calculate this real quick. 20 sine of 10 degrees. It works out to be about 3.4729. We're going to go to two significant figures here, so it's about 3.5. So 3.5 newtons would be the frictional force. And the cosine of 10, really we're trying to find this here, and really we're trying to find this down here. The normal force is going to be 20 cosine 10. And that's really going to be 19.69, so about 19.7 newtons. Okay, and I guess in this particular situation, we can't say 20 because this is 20, so this problem would be better suited to three significant figures. So to kind of change up my answer up here, I would probably go 3.47. Okay, so 3.47, 19.7, those are what would be represented by friction and the force, the normal force. So if we go back to our original slide here, we would say that the force of friction is therefore equal to 3.47 newtons. The force normal was equal to 19.7 newtons, and the force of gravity was equal to a negative 20.0 newtons. The last thing you'd want to do in a problem like this is, because the object is stationary, we can calculate the coefficient of static friction. Now, friction, if you remember, is essentially the coefficient times the normal force. And when we're trying to find the coefficient, we can write the equation as the force of friction divided by the normal force. Now it's newtons over newtons, so the units cancel. So in this particular situation, it's 3.47 divided by 19.7, and that gives you something in the neighborhood of, if you want to go ahead and calculate it, I'm calculating it right now. All right, hopefully you can check your answer with mine, 0.176. Now that's a very low coefficient, which means that the object would, if it was stationary at 10 degrees and it was just about to break into movement, that would be the coefficient, which would be very, very low. Please understand that when we calculate the coefficient of static friction, that is the coefficient, that is the force, or that is the coefficient between the two surfaces. But the force of friction, in theory, is the force it takes to, at just the moment that the object breaks free. So if we can raise this object any higher and it stays stationary, then this coefficient is going to get greater. It's going to go up. Okay, we're saying that this object is stationary only at its 10-degree point, and that if we were to raise it even an increment higher, it will begin to move. Okay, so that's how you do a problem where you have a block on a stationary block on a ramp, and you can apply this to different types of degrees. You can provide it to different masses and whatnot. I hope this helped to explain a lot. And if you have any questions, you can email me. Otherwise, have a good day.